Hi everyone, today I'm going to solve a question on finding electric field and electric potential created by a thin plastic rod that is bent into a shape of a semicircle. So let's read the question. A thin plastic rod that is 15 centimeters long carries 4.2 nanocoulomb charge. It is bent into a semicircle and you're asking for the electric field and electric potential at the center of that semicircle. So let's draw the semicircle in here. So I have a rod, but I turn it into a semicircle. So this is my semicircle, and I'm going to draw my X and my Y axis in here. So the length of this semicircle, which is basically the arc length, it is equal to 15 centimeters, and you can convert that into meters. So that's going to be 0.15 meters. The charge on this rod that is bent into a semicircle, it is equal to 4.2 nanocoulomb. You can convert it to coulomb by multiplying it by 10 to the minus 9. So we have the charge on it too. Perfect. So we are looking for the electric field at the center of the semicircle first. And what are we going to do? If you remember, at our exam prep session, we said if you have a continuous charge distribution, like a rod that I have in here, what you need to work on is basically an element of charge on your rod. So I'm going to take an element and I'm going to call it dq. That's what we did in our exam prep session. And if you remember, we said you're going to need to create a dE such that that dE equals, if you remember, k dq over r squared. Yeah, so r in this case, if I look at this element and this element is located at a distance r, the radius of the semicircle from the center at which you want to calculate the electric field, so therefore dE, that's the electric field created by that little element of charge, it is equal to k dq over r squared. Yeah, okay. So you're not provided with the radius of the semicircle, and where we can find it in terms of L. Yeah, we will talk about that soon. But first I want to find dq. Yeah, so I want to find dq. Everybody, we talk about this in the class. Everybody knows that if you have a line of charge, instead of having a surface density, we have a line density. If you're wondering what a line density is, we talk about it at the prep session as well. A line density, lambda, it is equal to basically Q divided by the length of the line of charge, and we have a rod in this case in here. Yeah, so lambda equals Q over L. And if I look at it, if you look at it, the arc length is L. And if you want to write the arc length L in terms of lambda and L in terms of R, isn't that L equals R times the pi? Yeah. Do you remember from advanced function, the arc length equals the radius times the angle. The angle for the arc length here, it is pi. So therefore here my lambda equals Q over pi times R. That's my lambda in terms of the charge and the arc length. Okay, so now I want to come up with dq. What would be dq? dq, though, if I isolate this equation for q equals lambda times L. Therefore, dq equals lambda times dl. Look, linear charge density, lambda, is always a constant number. But the arc length that is covering dq, let me show you. dq is that little element. The arc length that's covering this dq, it is equal to basically this dl. So can I call this one dl? Yeah. So it's not the whole length of the rod, it's just that little dl. Yeah, so that's why dq equals lambda dl. And if we want, instead of dl, can I write lambda r d theta? Again, I'm using the arc length. So if L is r times a pi, dl equals r times d theta. Good. What is d theta? If you're wondering what d theta is, it's that little angle. Yeah. So that is d theta. Good. If you want, even you can put it right in there because soon I'm going to draw the electric field. That's my d theta. Good. So having dq, then I can sub that into the equation for the electric field. So if I go back to this equation, DE equals K. Instead of dq, I can write lambda r d theta over r squared. Does that make sense? Where you can cancel out one r from the top and one r from the bottom, you end up getting K lambda d theta over r squared. Does that make sense? Okay, so now we have the electric field that is created by the little dq. So this dq, because the charge on the semicircle is positive, this dq at the center is going to create an electric field dE along the line of r, but going away, starting from the center, going away from the charge. So that is actually my dE. That's a dE that I have the equation for written in here. And if I look at another dq, feel free to look at another dq. If I take another dq on the semicircle, that other dq is going to create an electric field going that way because it's a positive charge. Connect the positive charge to the point at which you want to calculate the electric field, and then start the electric field from that point. And the electric field is pointing away. It's pointing away from the charge. So that's another electric field I have from this little charge. So now if you break up each electric field into x and y components, so I'm going to break up this dE into dEx and dEy. I'm going to do the same thing with the other dE. So I'm going to break that one into dEx and dEy. You guys see that the x component of the electric field, they kind of cancel out each other. So you don't have to deal with the x component. So can I figure out the y component? Of course I can figure out the y component. How? If I look at this dq, its angular position with respect to the positive position of the x-axis is theta. Isn't it? So its angular position is theta. If this is theta, do you guys believe that this is theta as well? Therefore, the x component of the electric field would be adjacent, and it will take the cos. And then the y component, though, the y component of the electric field would be opposite. Yeah, this is the y component, which is right in here too. And therefore, it will get the sign. So I can say, look, dEy equals dE sine theta. Yeah? By breaking dE into two components and ignoring the x components because they cancel out each other, I have dEy equals dE sine theta. Now I'm going to sub in for dE. I had k lambda d theta over r squared times sine theta. There you go. We're almost there. Good. So that's my dEy. In order to find the total electric field, which is basically the sum of all these y components of the electric field, what you do, you just take the antiderivative of both sides. So let me write dEy one more time. dEy equals k lambda d theta sine theta over r squared. If I take the antiderivative of both sides, yeah, so you will have Ey, which is basically that's your net electric field because the x components, they are gone. They cancel out. So k lambda And sorry, I had a r in here because that r squared was cancelled with r in the top, so you ended up having r. So can I factor out that k lambda over r? And I mean, I bring it out of the antiderivative. So you end up having sine theta d theta, the antiderivative of sine theta d theta. So if I look at my arc, don't you guys believe that theta starts from 0 and it goes to pi because you're covering a semicircle, a half a circle. So I can say, look, my theta is from 0 to pi. And then I will end up getting k lambda over r. The antiderivative of sine is a cos. So cos theta from 0 to a pi. Yeah? So it's actually a minus a cos. So I can put the minus sign in here. So your net electric field is equal to minus k lambda over r cos of pi minus cos of 0. So cos of pi is basically minus a 1 minus cos of 0, which is 1. You end up getting minus 2. Therefore, you will have 2k lambda over r because the minuses would cancel out each other. Perfect. Good. So I do not have lambda. Lambda is not given. What you're given are basically Q and L. Maybe somehow I can convert my lambda and R to Q and L. Does that make sense? So what I do, I have E net equals 2 times K. Well, my lambda was Q over pi R, wasn't it? So instead of lambda, I'm going to put Q over pi times the r, and I have another r in there. So it becomes pi r squared. Does that make sense? Perfect. So I'm almost there. I just need to convert the r to L. So if you remember, r is equal to L over pi from this equation. So can I, instead of r squared, can I use L over pi squared? And if you do the math, you rearrange, you expand that, and you rearrange, you will get 2kq times the pi over L squared. And then you have all the numbers. You have q, you have L, you have pi, you have k. E net, if you sub in the numbers, E net will be 1.17 newtons per coulomb. Yeah? So the key to solving this question is to take an element of charge known as dq in there and figure out lambda in terms of q and L, also figure out dq in terms of lambda and L, create a dE, the element of electric field, and then figure out the component, the y component of the electric field, take the antiderivative of both sides, and then you will have the net electric field. Good?